So section 2.4 introduces two new derivative rules. And the first of the two I'll just start with. The first kind of derivatives that we're going to work with are derivatives of exponential functions. And to be an exponential function, there should be an x in the exponent. And these are pretty easy derivatives to do. So these would just be common, simple examples of exponential functions. And I'll just write down a handful. Maybe like f of x equals 3 times 2 to the x squared plus 6x plus 7, or f of x equals 5 to the 7x, or f of x equals 6e to the, how about x cubed plus 7x squared plus 5x minus 4. So these are all exponential functions, specifically because the x's are all stuck in the exponents. The middle problem, I don't have a coefficient. The base is 5, but there's not a coefficient. There's an implied coefficient of 1 here. This is really the same as 1 times 5 to the 7x. So each one of these is just a simple exponential function, and derivatives of exponential functions are super easy. To find the derivative of an exponential function, you simply multiply the coefficient by the derivative of the exponent times the natural log of the base, and that's probably too fast. So for the derivative of an exponential function, it's just going to be the coefficient, which is the number to the left of the piece with the exponent, times the natural log of the base times the derivative of the exponent times the original exponent part. I don't know that this is written, so I don't know the right word to use right now. Exponential part. Exponential part. So if I looked at the examples that I had written on the previous page and I wanted to find their derivative, the first example I just made up was f of x equals 3 times 2 to the x squared plus 6x plus 7. For the derivative, I'll just kind of use this rule, but maybe I should identify the pieces. So for this particular problem that I made up, the coefficient, that's the number in front of the exponential piece, but the exponent doesn't apply to it. So in this particular problem, the coefficient is 3. The exponent of x squared plus 6x plus 7 only applies to the 2. The number that the exponent applies to is called the base. So in this case, the base is 2. And then the exponent is x squared plus 6x plus 7. But I need the derivative of the exponent, so let me write that down. So the derivative of the exponent, I'll just take this derivative. The derivative of x squared is 2x. The derivative of 6x is 6. The derivative of 7 is 0. So when I go to write down the derivative, I have the coefficient of 3, the natural log of the base is going to be 2. I'm going to put the natural log of 2. For the derivative of the exponent, I'm going to put 2x plus 6. And for the original exponential part, that's this. I didn't really know how to write that maybe in nice math words. But the original exponential part, piece I'll call it now, is the 2 times x squared plus 6x plus 7. When there's a coefficient, the base probably should be in a parentheses, otherwise this might look like the number 32 as opposed to 3 times 2 to that power. So now I'm just going to write the derivative down. So the derivative of this exponential function, sorry I went off the screen a little bit here, the derivative of this exponential function is going to be first the coefficient, which is 3, and then times, I'm not going to use a times sign, it's going to be implied when I write the ln of the base next to the 3. I could have put a times sign like I had in the little explanation up here, but that times is implied. So 3 times the natural log of 2, that's the coefficient, times the natural log of base. Now times the derivative of the exponent. I'm going to put that in a parentheses. And it almost looks like the 2x plus 6 is attached to the ln, so maybe I should write this in a different order. I'll finish it up and then I'll write it in an order that might be less confusing. So coefficient, natural log of the base, this is the coefficient, this is the natural log of the base, this is the derivative of the exponent, and then times the original exponent part, which is 2 to the x squared plus 6x plus 7. In my little write-up here, I should have maybe flip-flop these orders here and do the coefficient times the derivative of the exponent times the natural log of the base times the original exponent piece. So this would be a complete derivative. There's a common factor of 2 there that I probably should factor out. And if I factor out a 2, I'd multiply the 2 that I factor out by the 3 that's already there. If I factor out a 2 from this, I divide both numbers in the parentheses by 2 and get an x plus 3, and then I'm running out of room. And then the natural log of 2 times 2 to the x squared plus 6x plus 7. So if I was writing a derivative for this exponential function, I'd say the derivative is probably 6 times x plus 3 times the natural log of 2 times 2 to the x squared plus 6x plus 7. And that would be probably the nicest derivative that I could come up with for this particular function. One big deal when you're taking the derivative of exponential functions, the exponent doesn't change. The exponential piece stays exactly the same. You get the whole exponential piece back and you just get some things before it. On this second example that I wrote down, if I wanted to do the derivative of that exponential function, I need to know what the coefficient is. The coefficient's the number in front of the exponential piece, and there's an implied 1 there. When the coefficient is 1, I probably am not going to include it in my answer because multiplication by 1 is not needed to write. So I need the coefficient. I need to know what the base is. In this case, the base is the number that the exponent applies to. So the base is 5. And then I don't need to know the exponent. I need to know the derivative of the exponent. And the derivative of the exponent is 7x. The derivative of the exponent is just 7. And the exponential part, the exponential piece, is the whole function 5 to the 7x because there isn't a coefficient. So And for a derivative, I'm going to start doing this. I'm going to say the derivative of an exponential function is the coefficient, and I'm going to flip-flop the order, times the derivative of the exponent times the natural log of the base times the original exponent piece. So for this particular function written in number 2, I'm going to say the derivative of this function f is the coefficient. I'm not going to include the coefficient because it's a 1, times the derivative of the exponent. The exponent was 7x. The derivative of the exponent is 7. Technically, I could have a 1 written first, but I'm not going to write it for the coefficient. For the derivative of the exponent, just 7. For the natural log of the base, times the natural log of 5. And then times the original exponential piece. The exponential piece is 5 to the 7x. And that would be the entire derivative for that problem 2. For this problem 3 that I wrote down, if I wanted to find its derivative, I need to know the pieces. The coefficient is this number 6. The base is e. Notice I didn't put a parentheses here. The times is implied. And because the 6 isn't included in a parentheses that's attached to the e, the 6 is not considered part of the base. It's considered the coefficient. So I need the coefficient, the base, the derivative of the exponent. The derivative of the exponent, I'm going to take the derivative of each term here. The derivative of x cubed is 3x squared. The derivative of 7x squared is 14x. The derivative of 5x is 5. And the derivative of minus 4 is 0. And the exponential piece, I don't know if I can fit it here, is this e to the x cubed plus 7x squared plus 5x minus 4, kind of out of room. So now I'm going to write down the derivative of this function by just taking the pieces that I have here and writing them down and calling it a derivative. So I'm going to say the derivative f prime of x equals first the coefficient of 6 times the derivative of the exponent. The derivative of the exponent is 3x squared plus 14x plus 5 times the natural log of the base. The base is e, so times the natural log of e. And then times the original exponential piece, which is the piece everything but the coefficient. So times the e to the x cubed plus 7x squared plus 5x minus 4. Basically done, although this part's written kind of cruddy. The only trick is that the natural log of e is equal to 1. So if I did natural log of e on my calculator by going second and divide, natural log of e is equal to 1. So for this piece right here, this piece is equal to 1, so I can replace it with a 1. And multiplying by 1, you just get everything but that 1 back. So a better form for the derivative here would be f prime of x equals to 6 times 3x squared plus 14x plus 5 times 1, which I'm not going to write, times the e to the x cubed plus 7x squared plus 5x minus 4. All right, that's everything to get us halfway through the section. There are going to be some of the exponential problems that we'll have to use the product rule because the number, or in front of the exponential piece, will have an x, and we'll have multiplication where both pieces have an x, and then all of a sudden we need to use the product rule, but not yet. So for problems 1 through 32, just doing a bunch of exponential derivatives. To do an exponential derivative, I need to know the coefficient. If there isn't a number lifted to the left of the exponential piece, the coefficient is assumed to be 1. You won't need to include it in the answer. You need to know the base. In this case, the base is e. I need the derivative of the exponent. The derivative of 7x is just the number in front of the x, which is 7. And the exponential piece, well, the whole piece is the exponential piece here because there isn't a coefficient. So the derivative of this is going to be the coefficient times the derivative of the exponent times the natural log of the base times the exponential piece, and the exponent doesn't change for these derivatives. So let me just write this down. Y prime equals, I don't need to write the coefficient because it's 1. Now I'm going to write the derivative of the exponent, which is 7, times the natural log of the base, don't need a times sign, that's going to be implied, times the exponential piece. So coefficient not necessary, derivative of the exponent 7, natural log of the base, and then times the exponential piece. When I'm doing e derivatives, I don't need to include this piece because the natural log of e is equal to 1. So I'm going to skip that piece because I don't need to show something that's equal to 1. Just like I didn't show the coefficient of 1, I'm not going to show the natural log of the base part when the base is e because that's equivalent to 1 as well. So my answer for the derivative in problem 2 is just going to be 7e to the 7x. So you should be able to do something similar. And then hopefully you can start doing these derivatives way faster. So I'm going to do number 4. The coefficient would be the number that's implied in front of the exponential piece, which is 1. The base is e. The derivative of the exponent, well, it's the derivative of 9x minus 1. The derivative of 9x is 9. It's a first power term. The derivative is just the number in front of the x. The derivative of the minus 1 is 0 because it doesn't have an x. And the exponential piece is e to the 9x minus 1. So when I go to write the derivative of this with a little prime symbol, coefficient I don't need to write, but I could. Natural log of the base I don't need to write because it's equal to 1. Oh, I kind of flip-flopped the order, but it doesn't matter here. Times the derivative of the exponent, which I said I was going to write here. So let me do that. Coefficient, derivative of the exponent, natural log of the base times the exponential piece. This piece, I don't normally write the coefficient when it's 1, and I don't write the natural log of e because that's also equal to 1. So replacing the natural log of e with 1, I get 1 times 9 times 1, and you get 9e to the 9x minus 1. So real quickly, when we're doing derivatives with e's, I'm not going to worry about doing the natural log of the base piece because it's going to be equal to 1. So when I go to do the derivative of an e, I'm just going to go coefficient times derivative of the exponent times the exponential piece. So the shortcut for e, when e is the base, so when the base of an exponential function is e, we can skip the ln of the base when writing the derivative because it equals to 1. So for these derivatives, I'm just going to do coefficient times the derivative of the exponent times the exponential piece. And these first two problems don't have coefficients, so the coefficient part is 1. So for problem 6, if I want to do the derivative, I think I can do it without writing any side work. So for problem 6, I'm going to write the derivative equals, the coefficient is 1, so I don't need to write the coefficient. So it's 1. I'm not going to write a coefficient when it's 1. And then for my derivative of my exponent, the derivative of 7t squared is 14t. The derivative of minus 3t is minus 3. The derivative of 1 is 0, so that's the derivative of the exponent. And then the exponential piece is the whole function because there isn't a coefficient here. This will never simplify. I can't multiply something with an exponent by something that doesn't have exactly the same exponent. So that's the whole derivative. So e's are supposed to be way, way quick derivatives to take. So I'm going to do 8 now. It's the first one that I've written with a coefficient. Here, the coefficient is 8. The base, how about we do the derivative of the exponent first? The derivative of the exponent, the derivative of 2x, because it's a first power term, is just a number in front of the x, which is 2. And the derivative of the 5, since it doesn't have an x, is 0. So the derivative of the exponent is 2. The base is e, so I don't need to include the ln of the base part. And the exponent piece is the part without the coefficient. So again, the derivative of an exponential function, it's the coefficient times the derivative of the exponent times the natural log of the base, which I don't need to write here because the base is e and that's equal to 1, times the exponential piece. So when I go to write down the answer to problem 8, I'm going to write down the derivative is the coefficient, which is 8, times the derivative of the exponent, which is 2. I'm not going to write times the natural log of the base because the natural log of the base is equal to 1, so I'm going to skip that part because it's an e function, and then times the exponential piece of e to the 2x plus 5. I didn't put this 2 in a parentheses because it wasn't a binomial. I'm going to multiply the 8 and the 2. So it's important that the exponent doesn't change. So your 7 should work the same way. Now we're into the grunge part, because to the left of the exponential piece, there is a x. So the coefficient in some sense has a variable. Now I have to treat this with a product rule. Let's do 9 and not 10. So 9, when I look at this, there's multiplication. Y equals x squared. So in some sense, the coefficient is x squared. When the coefficient when to the left of the exponential function, there's an x, you have to use the product rule. So here there's multiplication that's implied when the x squared is left to the left of e to the x. There's multiplication. Both factors have an x. I need to use the product rule. To use the product rule, I have to write down the first factor. In this case, that's the x squared. And the second factor. In that case, it's an e to the x. Then I need the derivative of the first factor. The derivative of x squared is just 2x. And the derivative of the second factor. And to do the derivative of this e to the x piece right here, if I'm looking at this piece right here and trying to find its derivative, this is really 1e to the 1x. So to do its derivative, I have to know the coefficient. And the coefficient here is the implied number in front, which is 1. I need to know the derivative of the exponent. The exponent is 1x. It's a first power term, and the derivative of any first power term is just the number in front of the x, which is going to be 1. The base is going to be e, and the exponent piece is e to the x. So when I go to write down the derivative of this, it's technically the coefficient, 1, which I shouldn't write, times the derivative of the exponent, 1, which I shouldn't write, times the natural log of the base, which is also equal to 1, that I shouldn't write, times the exponential piece, e to the x. So this is really 1 times 1 times 1 times e to the x, and that's just going to be e to the x for that derivative of the second. So now I can bust out the product rule. The product rule says I do first factor times the derivative of the second plus second factor times the derivative of the first. So when I go to write the derivative here, I'm going to write first factor, x squared, times derivative of the second, which is e to the x, plus second factor, which is e to the x. I'm not going to bring these ones down, times derivative of the first factor, which is 2x. I should probably write it before as opposed to after. It's going to make it easier for me to do the work. So a lot of times when I'm using the product rule, I flip-flop these. Rather than writing e to the x times 2x, I'd probably write it in an opposite order. Let me pull out a common factor. There is a single x term for both pieces. And let me just write this better. Right now I should have written y derivative equals y squared, x squared e to the x plus 2x e to the x. And in terms of a common factor, between this x squared and that single x, I could factor out a single x. And both pieces have an e to the x, so I can also factor out an e to the x. So the common factor is going to have a single x and an e to the x. From this first piece, there were two x's. I factored out one. I'm left with 1x. There was an e to the x. I factored it out, so it's gone. After the plus sign, I factored out the x, so it's gone. I factored out the e to the x, it's gone, but this 2 remains. This would be somehow the best answer for problem 9. All right. Ugh, yuck. All right, I kind of got out of control here a little bit. So let's do, I'll do 12, you can try 11. My video's got to have to hiccup soon. So it's multiplication. Both pieces have a letter. I need to use the product rule. So in number 12 that I'm about to do, the first factor is 2y minus 3. The second factor is e to the 5y. The derivative of the first factor, the derivative of 2y is just 2, the derivative of minus 3 is 0. And for an e function that doesn't have a coefficient, the quickest way to write down its derivative is just take the derivative of the exponent and write it to the left of the function. Because for this e function, this e to the 5y, it's really 1e to the 5y. Technically, the coefficient is 1. The derivative of the exponent, the derivative of 5y, is just 5. The base is e, and the exponential part is e to the 5y. So its derivative would be the coefficient of 1 times the derivative of the exponent, 5, times the natural log of the base, which is equal to 1, times the exponent part. So this is going to be 1 times 5 times 1 times e to the 5y. It's just 5e to the 5y. The shortcut of doing a derivative of an e without a coefficient is just write the derivative of the exponent to the left of the e function. So these are the 4 pieces I need. First factor, derivative of the first. Second factor, derivative of the second. So when I go to write my derivative, put the little prime symbol. I'm going to do first factor, 2y minus 3, put it in a parentheses because it's a binomial, times the derivative of the second. I'm going to write it just because I did leave myself some room, but I probably should have written it first, but it doesn't matter. Derivative of the second, plus second factor e to the 5y, times the derivative of the first, which is 2, and I wrote it kind of in a nicer order. There's a common factor of e to the 5y that I'm going to factor out, and that's going to give me f prime of y equals common factor of e to the 5y, because they have both pieces have an e to the 5y. When I factor out the e to the 5y from the first piece, I'm left with 2y minus 3 times 5. I'd love to have that 5 written to the left of the parentheses. And after the plus sign, I'm left with a 2. I'm going to clear this inner parentheses, combine like terms, and get a best derivative. So this is going to be e to the 5y times, now to clear this parentheses, I'm going to go 2y times 5 is 10y, minus 3 times 5 is minus 15, and then plus 2. Now I'm going to combine like terms. And I think this is going to be 10y minus 13 if I combine the minus 15 and the plus 2. And you should just be using your calculator if you're not good doing that arithmetic in your head. Alright, so your problem 11 should be very similar. My lord, there's a lot of these. Alright, let's just keep mushing on. I'm going to do 13 for you. Pause the video and give it a try if you want. Otherwise, watch me do it if you're not ready to do it. Multiplication again. Both factors have a x, so I need the product rule. So my first factor is 3x minus 4 squared. My second factor is e to the 5x. Now I need the derivative of each. First factor is a parentheses with an exponent, so I need to use the chain rule to find its derivative. I bring the exponent out front, I leave myself some room, lower the exponent by 1. So to find the derivative of the first factor, because it's a parentheses with an exponent, I use the chain rule, bring the exponent down, leave the contents of the parentheses the same, leave myself some room, lower the exponent by 1, and where I have that room, write the derivative of each term inside the parentheses. The derivative of 3x is 3. The derivative of minus 4 is 0. So for the derivative of the first, I'm going to write 6 times 3x minus 4. Now I'm going to do the derivative of the second. And I'm going to shortcut it. To do the derivative of an e that doesn't have a coefficient, it's just the e function times the derivative of the exponent. So the shortcut for an e function without a coefficient, it's just the derivative of the exponent times the exponential piece. Because the other two pieces, the coefficient is 1 and the natural log of the base is 1. So I don't need to write those pieces. Of the 4 pieces, 2 of them are 1, the coefficient and the natural log of the base. So I'm going to write the derivative of the exponent. The exponent is 5x, its derivative is 5, and the exponential piece is e to the 5x. So those are the pieces I need. I'm going to multiply these, and then pull out common factors. So now I'm going to write the derivative equals first factor, 3x minus 4 squared, times the derivative of the second, and I'm going to flip-flop the order. Sometimes it's just easier if I backwards the order. This is the first factor times the derivative of the second, written in an order that I think is going to make it easier to factor. And then plus second factor times the derivative of the first. Second factor e to the 5x, derivative of the first 6 times 3x minus 4, and now I'm going to common factor. For both parts, there's an e to the 5x, and there's a factor of 3x minus 4. So I'm going to factor out an e to the 5x, and between the 3x minus 4s, there's 2 of them here and 1 of them there. I need to factor out the smaller number, and that's the 1 of them. So that's my common factor. From the first piece to the left of the plus sign, I didn't factor out this 5. I factored out the e to the 5x, so it's gone. I factored out 1 of the 3x minus 4, so I'm still left with another 3x minus 4, so our 3x minus 4 to the first power. To the right of the plus sign, I factored out the e to the 5x and the 3x minus 4, but I didn't factor out the 6. Inside this parentheses here, I'm going to make this 15x minus 20 plus 6 by clearing that parentheses, and then I'm going to combine like terms. So my answer for number 13 would have an e to the 5x, a 3x minus 4, And then in that last parentheses, I'm going to combine the minus 20 plus 6 and get a minus 20 plus 6 and get a minus 14. In that last parentheses, a 15x minus 14. All right. Oh my Lord. Well, we're going to be skipping a few of these, I think. The video's already getting kind of long. Let's do this one just fine. I think we can do these. You can try 15. I'll do 16. Multiplication, both factors have an x, so I need the product rule. So for my 16, my first factor is going to be x squared minus 3x plus 1 cubed. My second factor, e to the 2x. Now I need to do the derivative of the first. The first is a parentheses with an exponent, so I need a chain rule. I'm going to bring the coefficient out front. I'm going to leave myself some room, and then I'm going to lower the exponent by 1. Where I left myself some room, I'm going to put the derivative of each piece inside the parentheses. The derivative of x squared is 2x. The derivative of minus 3x is minus 3. The derivative of 1 is 0. For the derivative of the second, it's an e function without a coefficient, so the derivative is just the derivative of the exponent times the original function. So again, e's, because in this piece, because it would be the derivative would be the coefficient times the derivative of the exponent times the natural log of the base times the original, the exponent piece. And the coefficient is 1, and the base is 1, and I don't need to write either of those pieces because they're both equal to 1. So for the derivative here, I just need the derivative of the exponent, which is the derivative of 2x, which is just 2, times the exponential piece, which is e to the 2x. So when I go to write my derivative down now, it's first factor times derivative of the second factor. First factor is x squared minus 3x plus 1 cubed. Instead of writing the derivative of the second factor after it, I'm going to write it before it. So that's first times derivative of the second plus second times derivative of the first. Ugh. So second times derivative of the first. Now I'm going to common factor. Both parts have an e to the 2x, and both parts have that parentheses with an exponent, and I'll factor out the smaller exponent of 2. So when I go to do my simplifying by common factoring, I take the e to the 2x part and the parentheses part that's in common, but with the smaller exponent. So that's my common factor. And now I'll figure out what's left. To the left of the plus sign, I'm left with that 2. The e to the 2x is gone. I had 3 of these. I factored out 2, so I'm left with 1 of those. To the left of the parentheses, I have a 2 and that to the first power, because I started with 3, I factored out 2. After the plus sign, I factored out the first and the last piece, the e to the 2x and the parentheses with the square. I'm just left with the 3 and the 2x minus 3 in the middle. Now I'm going to clear these parentheses and combine like terms. So the first parentheses, when I clear it, I'm going to get 2x squared minus 6x plus 2. The second parentheses, when I clear it, I'm going to get 6x minus 9. I'm going to combine those terms that I have written in blue. The 2x squared is just going to hang out. There's not another x squared term there. The minus 6 and the positive 6x are going to cancel, and the 2 minus 9 is going to give me negative 7. And that's the best I can do for an answer to problem 16. I think I'm going to do a couple skips here. Yeah. So at least let's skip 17 and 18. You can give them a try if you care to. E's with negative exponents, maybe not the most important problem. Similarly, let's skip 19 and 20. These are more complicated than anything we'll ever see for the semester, and you won't see these in Math 218 at this level of difficulty. So you can give those a try. Check my solutions manual if you want to just, try them, but you don't have to do them. A few more, and then we'll get into a part 2 of this video. Few more. Too many more. So problems 21 and 22 are division, and for division we need the quotient rule. The quotient rule, remember, it's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. So in order to do 21 or 22, it's a fraction, I need the quotient rule. I'm going to do 22. My denominator is e to the t. My numerator is t cubed. The derivative of the denominator, it's an e without a coefficient, so the derivative is just the derivative of the exponent times the e function. I don't need the natural log of the base, and I don't need the coefficient because they're both 1. The exponent is 1t, and the derivative of 1t is just 1. So the derivative of that piece is just the derivative of the exponent times the exponential function. It's just e to the t, or 1 e to the t. The derivative of the numerator is 3t squared. So when I go to write down my derivative for problem 22, I'm going to write down the denominator, e to the t, times the derivative of the numerator, which is 3t squared. Probably I want to write, it doesn't matter, times 3t squared, minus the numerator, t cubed, times the derivative of the denominator, e to the t, all over the denominator squared. So that's the derivative, just not simplified. In the numerator, I'm going to pull out some common factors. On either side of the minus sign, there's an e to the t, and on either side of the minus, there's a t term that doesn't have an addition associated with it. So I'm going to pull out a common factor for these. For the e to the t, the common factor is just e to the t. For the t squared and t cubed, I need to factor out a t squared, the smaller exponent. What's going to be left? To the left of the minus sign, I factored out the e to the t and the t squared. I'm just left with the 3. After the minus sign, there were 3 t's. I factored out 2, so I'm left with 1 t, and I factored out the e to the t. In the denominator, if instead of writing it with an exponent, I write it with repeated multiplication, it's going to make the canceling easier for me to do. E to the t squared is e to the t times e to the t, and that's going to make it so the common factor of e to the t will cancel with one of the e to the t's. And this is going to give me where I'm going to stop for an answer. It's going to give me the derivative equals t squared times 3 minus t, which you could actually write with the t first and factor out a negative, but I'm not going to do that. So t squared times quantity 3 minus t over e to the t would be the perfect derivative. Let's do 21 with you, just in case you need to see it, because I'm not going to do 23 and 24. So if you are working with 21, I need to know the denominator, the numerator, the derivative of the denominator. It's an e term without a coefficient, so the derivative is just the e function. and times the derivative of the exponent. The exponent is 1t. The derivative of the exponent is 1. So to do this derivative, you take the derivative of the exponent, the derivative of t. It's a first power term. The derivative is just the number in front of the exponent, in front of the t, and then times the exponent. So it's derivative of the exponent times the e piece. And then the derivative of the numerator is going to be 2t. So for the derivative, it's that fraction, start off with the denominator times derivative of the numerator. So e to the t times 2t minus numerator times derivative of the denominator. I'm not going to write the 1 here. I'm just going to write e to the t. All over the denominator squared. Now common factor. In the numerator, there's a common factor of e to the t because both pieces on either side of the minus sign have an e to the t. And there's a common factor of a single t because there's a t on either side of the minus sign. So I'm going to factor out an e to the t and a t, write my parentheses. To the left of the parentheses, for the first piece I'm left with a 2 because I factored out both the e to the t and the t. After the minus sign, I factored out the e to the t, but only one of the t's from the t squared, so I'm just left with 1. And again, I'm going to write the denominator with the e to the t written twice. I'm going to cancel out the common factor of e to the t with one of the e to the t's in the denominator. And for an answer, I'm going to write t times 2 minus t over e to the t. Okay, getting really deep into a long lecture here. Let's go ahead and skip. These are just uglier than we'd need. In Math 220, calculus kind of for engineers, this would be maybe more appropriate. So just a few more problems and we'll punt on this part of the video. Let's see what we can do with these. So 25 and 26 are exponential functions. The base isn't e. So for the derivative, it's the coefficient times the derivative of the exponent times the natural log of the base times the exponential piece. And in problem 26, this is really 1 times 7 to the x. There's not a coefficient that's written, so there's an implied 1. The exponent is just x. The derivative of just a single x is the number to the left of the letter. That's an implied 1. For the natural log of the base, I'm going to write the natural log of 7 because 7's the base. And the exponential piece is just 7 to the x. There's going to be 4 pieces in my derivative. Coefficient, 1 that I don't need to write. Derivative of the exponent, 1. Natural log of the base, natural log of 7, and the exponential piece. So the derivative in problem 26 is just going to be the natural log of 7 times 7 to the x. I probably don't really need a times sign there, but I can put it there because the other pieces are 1. For 28, it's an exponential function. I need to have the coefficient times the derivative of the exponent times the natural log of the base times the exponential piece. And again, in problem 28, there's not a coefficient written, so it's assumed to be 1. When I go to write the derivative for problem 28, if I want to write the coefficient, I'd write 1. For the derivative of the exponent, it's the derivative of 2x, which is just 2. The natural log of the base is going to be the natural log of 7 because the base is 7. And the exponential piece is 7 to the 2x power. I can't really simplify this other than multiplying the 1 and 2, and I shouldn't even have written the, probably shouldn't have even written the 1. I don't need to put times sign between the individual pieces, but I could. So I would call that the derivative for 28. Let's do 29 together, skip 31 and 32, and call that the end of this half of the video, because we're already pushing an hour. So let's do 29. So 29's multiplication in both pieces have an x, so I need the product rule. So I need the first factor, which is going to be 3x. Second factor, which is 2 to the x. I need the derivative of the first factor. It's a first power term. Its derivative is just a number in front of the letter. I need the derivative of the second factor. And for the 2 to the x, this is really 1 times 2 to the x. Its derivative is going to be the coefficient. Don't need to write it when it's a 1, times the derivative of the exponent. The exponent's just 1x. The derivative of 1x is just a 1. It's the number preceding the x, times the natural log of the base. The base is 2, so I'm going to get a natural log of 2 times the exponential piece, which is the 2 to the x. So this derivative is going to be the natural log of 2 times 2 to the x, because I don't need the 1s. So when I go to write down the derivative for problem 29, I'm going to write the derivative is first factor 3x times the derivative of the second times the natural log of 2 times 2 to the x plus second factor 2 to the x times derivative of the first factor, which is 3. So first factor times derivative of the second factor times derivative of the first. Now I look for common factors. On either side of the plus sign, there's both a 3 and a 2 to the x. So I'm going to factor out both the 3 and the 2 to the x. I'm going to write the 3 first and the 2 to the x second. Write a parentheses. What's left after I factor out the 3 and the 2 to the x from the first piece is both an x and a natural log of 2. After the plus sign, I don't have anything left. I'm not allowed to leave an opening when I pull out a common factor. If I factor out something completely, I pull out a 1 for my common factor. So that would be the answer for 29. Let's go ahead and skip 31 and 32 and call this the end of the first part of section 2.4. And then for the rest of 2.4, we're going to be doing the derivatives of logarithms. And they're real similar. The derivatives of logarithms are hardly different than the derivatives of e's. They're just a little bit. They're not particularly hard to do. And then I might do a third part where we do some finding equations of lines that we kind of throw at the end of each of these sections.